Okay, so we're going to talk about three types of energy today. We're going to start with the first one. It says the energy of motion, or kinetic energy. Now, in terms of the labeling of this, I'm going to use this label. You might not see the same label in the textbook. It might be a different label, but as long as you understand what the label means, you should be fine. So the label I'm going to use for kinetic energy, because some books will use KE, some will use EK. I'm going to use big E, little k to stand for kinetic energy, okay? And the equation for kinetic energy is half the mass times the speed squared. Okay? Simple equation. I'm going to use this equation to answer the first question, right? Which is, how much kinetic energy does a car have at a speed of 20 meters per second? So the kinetic energy of this car would be a function of 1/2 times its mass, which has got to be in kilograms. So it's 2,000 times its speed squared. So 20 squared. So the kinetic energy of the car is 1/2 of 2,000 is 1,000 times 20 squared is 400. So that ends up being 40,000, right? 40,000 joules, or 4 times 10 to the, wait, that's 3, 2, should be 400,000, yep. Sorry, 400,000, or 4 times 10 to the 5 joules. Okay? There you go. We're done. Just kidding. We're not done. So that's the equation for kinetic energy, alright? But, you know, we talked about work is a change in energy. I don't know if we remember that last time we defined work as force times distance, or work is a change in energy. So today we're going to kind of connect that idea with, well, can you solve a question without force? And so you got a question and you have no force. But we have a type of energy, and we know it changes. So in this question here, we ask how much work is done to change the kinetic energy of a car from 20 meters per second to 10 meters per second. So you can see the energy of the car is changing because the speed is slowing down, right? So we can define work as a change in energy. Now delta means what? So E kinetic energy final minus kinetic energy initial, right? So that would be E K final minus E K initial, right? So that would be what then? Well, what's EK? EK is 1/2 M BF squared minus 1/2 M VI squared. That's your change in energy, right? So if you have a question where the kinetic energy is changing and you want to know what's the change in energy, you could set it up like this. And then you can actually simplify it, because we could factor out a 1/2 M, and you'll get this. You get VF squared minus VI squared. So there's your equation for work done with change in energy for kinetic energy. All right? Now, in this question here, so the work, which is the change in energy, is 1/2 the mass of the car, which is 2,000, times the difference in their speed squared, right? So it's going to be 10 squared minus 20 squared. Okay. So 1/2 of 2,000 is what? We already know it's 1,000. Times 100 minus 400 in brackets. So you end up getting negative 300,000 joules, or negative 3 times 10 to the 5 joules. Now, the negative sign means energy that had to be removed from the car. But here's the thing. You may have learned about something in grade 9 called the law of conservation of energy, right? So this is referring to the change in kinetic energy. So the negative sign means that the car has lost 300,000 joules of kinetic energy. That's what that means. But where do you think that energy went? Yeah, very good. Transfer to what? Well, what's stopping the car? Like, what's slowing it down? Brakes. The brakes of the car, right? So what force then is doing the work? Friction. So this is the energy removed by friction. So most likely it's going to be converted into probably heat. Right? It's got to be converted into something else. The amount of energy it gets converted to has to be 300,000 joules. That could be heat, it could be sound. Now, because of the law of conservation of energy, remember you can't create or store energy, you can only convert it from one form into another form. So this negative 300,000 just simply means that's how much energy has been removed in terms of kinetic energy, but it had to go somewhere else. That's a big concept, okay? Conservation of energy. That you don't really lose the energy, it's removed from one form, but converted into something else, okay? So we okay with kinetic energy, half mv squared? Alright, let's look at gravitational potential, which is the next equation. Okay, so the next equation is energy in relation to gravity relative to a height. And the equation for this, so I used EK for kinetic energy. I'll use E little g for gravitational potential. If you want to use your own subscripts, go ahead and use your own. And the equation is going to be mgh. Okay, mgh. Which means it's a function of the mass times g. Now, little g is 9.8 times the height of the object relative to the ground. This is relative to the ground, okay? All right. So, how much energy would be stored in a 10 kilogram object that is 5 meters above the surface of the ground? So that would be mass 10 times little g, which is 9.8, times 5. And that would be 98. That should be 490 joules. And by the way, the unit is the same because, actually, let's think about the unit for energy. It's what? A joule? Remember what a joule is? 1 joule is, what happened? 1 joule is a Newton meter, which is the same as what? Kilogram meter squared per second squared. And that's, when we look at the equation for kinetic energy, what was the equation again? It was mass, well, it was 1/2 mv squared, right? So we can see the unit here, because your mass is what? Kilograms? And then your speed squared is meters per second squared. So that makes sense. If you look at this equation, what's your mass in? Kilograms. What's g in? Meter per second squared. And what's height in? Meter. So you see it's the same unit, right? Because you got meters times meters, which is meters squared, over second squared times kilogram. Okay, so that's our second equation, right? But we'll do the same thing now we did with the first scenario. What if we change the height? You know how we change the speed? And we want to know the work done? What if we change the height? So in our second question, what if we take an object and, you guys okay? Can I move on to the next question? Okay. What if I take an object and I lift it from 2 meters from the ground to a height of 10 meters from the ground? Okay? So it's the equation, again, we can think of it as work is the change in energy, right? So wouldn't it be the same then as the potential energy at one point minus the potential energy at the other point? Because it's delta, right? So work is the change in energy. So energy would be, like, it would be mgh2 minus mgh1. That's the change in energy, right? And again, you can do the exact same thing we did before. You can factor out the m, or in this case the mg, and you can just say, well, the change in energy in this system is just a function of m times g times the change in height. But just like in the previous example, it was a function of 1/2 m times the difference in speed squared, right? Here it's the mg and difference in height. So how much work then is done to lift this object? So the work would be the change in energy, so it would be the mass times gravity times, well, we started at 2 meters, there's h1, and we ended up at 10 meters, which is h2, so it's going to be 10 minus 2. So how much work was done to lift this object 8 meters, basically? So 784? 784 joules. Okay? So in terms of the complexity of the equations, they're not very difficult. They're quite easy. Right? You have the equation for kinetic energy, and then you have the equation for potential energy, and then you also have the equation for work, which is just a change in those energy values, right? Okay, well, you're welcome. We'll do one more, and then I'm going to show you like a combo question, okay? So, if you recall, we looked at elastics. Now, do you remember the relationship between force and the amount of stretching or compression in an elastic body? It's linear, right? It's diagonal, actually, like this, right? Now, do you remember we looked at finding the slope of that line? And we had a particular name for it, right? We called it K, right? And K was F over X, right? K was F over X. Now, remember what K stood for? What was K? It was the constant of the spring. Yeah, it shows you the relationship between how much force to exert on a spring or elastic body and how much stretching or compression there is. The unit is Newton per meter. That was the unit for K. Now before I explain what that graph, kind of what you can get from that graph, I'm going to go back to something you did in kinematics, okay? Do you remember when we did velocity time graph? Now, if you recall, what is this pattern telling you? It's telling you that the velocity is what? Constant or changing? Changing, right? Now, if you took the slope of that line, what would you get? You get acceleration, right? Okay, so you get acceleration. Very good. So acceleration would be v over t. Just like k is f over x, a is v over t, right? What is x? X is the amount of stretching or compression. Okay? So if it's an elastic band, it would be stretching. If it was the springs in the car, it would be how much they get compressed. So you know when the car balances when you're riding, right? There's this compression going on in the spring. Now, if I said to you, what does the area give you? Very good. Now, why? Well, if you think about what's going on here, the area of that would be what? Base times height over 2, right? And that would be what? Velocity times time over 2, which is basically average velocity times time, which is, if you think about it, velocity is what? Meters per second times time, which is in seconds. That gives you meters, which is displacement, right? I want you to think about something. What does the area of this give you? Well, let's work it out. So if I had to write down the area as an equation, it would be what? Area equals F times X over 2, correct? Okay. Now, what's the unit for force? What's the unit for X? So what's Newton meter? What's a Newton meter? It's a joule. So what does the area under that graph represent? The energy of a spring. So the energy of a spring, so here's the thing, the energy of a spring can be written as, right, it's half, because you can see that it's just the same pattern as the velocity time graph. It's not a constant force. The force is increasing at a constant rate as you stretch or compress it. Now, there is another equation, because we could actually use, instead, we could use K, and I'll show you how we can use K in a second, right? But does that equation make sense to you? Because it's the same as the area under the velocity time graph, right? Sometimes you're not given the force, sometimes you're given just K. So like, for example, in this question here, we're just given K. We're not given the force. Now, we can work out the force very easily, because if you have K and you have X, if I have K and I have X, I can work out the force, right? Because remember, F equals K times X. And then we can go ahead and we can plug, because now, you have the force, you have the compression, you can plug it in. So we can do that here, right? So let's actually do that first. Let's say, what would be the force? So let's solve this two ways. One is, let's get the force. So what's the force? The force is K times X. So K is 1,000 newtons per meter, right? In this question, 1,000 newtons per meter. And X is 0.1 meter. So how much force is that? Well, that would be 1,000 times 0.1, which is 100 joules. Sorry, 100 newtons, not joules. Well, hold on. Now we're going to figure out E, because now we have F. Because our equation that we derived is Fx over 2. But I'm going to show you a different equation after, okay? So what we did here is we used the equation for springs that we learned before, which is F equals Kx. Solve for F, and then we're going to plug that back in and solve for E. So E equals Fx over 2, which is 100 newtons times 0.10 meter over 2, which is then 100 times 0.1, and it's a Newton meter, which is a joule, so 10 joules. Uh-oh, Nora, you tilted your head. That's never a good sign when you tilt your head. We divided by 2. Oh, sorry, I didn't divide it by 2, sorry. That's 5 joules. Sorry, 5 joules. We got to divide by 2. I'm getting ahead of myself. So it's 5 joules. Yes. Yes. Yeah, because the equation that we just came up with, right, the equation we came up with is the force times the distance over 2. So we solve for the force, and then we plug that in. But I'm going to show you an equation that you could use without having to do that. Yep. Right. Yeah, so yeah, basically we're looking at this equation which you learned before, F equals Kx, or K equals F over X. And then we have this equation on the left, which is E equals Fx over 2. Right, so we solve for force first, and then we plug that in. But there's a different way to do this. Like I need to give myself a little more room here. We have one more, and we're done. Yeah. So, but I'm going to show you actually a way to solve this question without actually even using force, just using K. Because I want you to go back to this equation. So we're going to go back to Fx over 2, right? Now, if I look at what F actually stands for, we have F equals Kx, right? Well, why don't we substitute for F then? Right? Well, why don't we say, well, if F equals Kx, let's put that here, and then get a different equation. So that if F is Kx, we have Kx times x over 2. So now that gives us Kx squared over 2. That should give us the same answer. So if we look at what we had before, if we use this equation, so we have Fx over 2, or we have Kx squared over 2, should get the same answer. So if we use this equation, well, okay, we have K is 1,000. X is 0.1, but it's 0.1 squared over 2. What do you get? You should get 5. You get the exact same. So now you have two different ways you can solve the energy of a spring, right? You can use Fx over 2 if you're given the force and you're given the stretching, or you could use Kx squared over 2 if you're given the K value. Most likely you will get the K value. Okay, now the last question is going to be an example of where we can convert one form of energy into another. All right? So this is the last question. And here it is. Yeah, it is a combination because we just looked at 3 different types of energy, right? We looked at the energy in a spring, we looked at the energy of motion, and we looked at the gravitational potential energy, right? So let's combine them. And we're going to keep this very simple and say that we're not going to lose any energy. In other words, it's not going to get converted into any other form. What I'm going to do is I'm going to set up a scenario where you have a spring, right? And you have a bead on a spring. The spring is compressed. So what kind of energy does it have? Elastic, right? Potential. The spring then shoots the bead. The bead goes flying to a maximum height. So what kind of energy would that be? Gravitational potential energy. And if I ask you a question, what's the maximum speed of the bead? That would be kinetic energy, right? So what we're going to do is we're going to look at converting one form of energy into another, but we're not going to lose any energy. And then we'll talk later on next week about, well, what happens if you do lose energy? Where does it go? Okay? Would that work the same way that when you look at the food that is not that it appears, but I'm not sure what you're asking. Okay. Actually, you could use this, the concept that I'm going to show you, you can actually use it for projectile motion. But we'll talk about that later. I don't know if maybe that's what you're thinking about. Okay, so let's look at this scenario. We're going to use the exact same spring. We're going to use the exact same compression. Okay? So we already know how much energy is in the spring, right? We worked it out that it was how many joules in the previous question. Okay. So we have a spring that's compressed, and there's a bead on it, and the amount of compression was 0.10 meters, and the K value was 1,000 newtons per meter. And we worked out that the energy, did I use EE? I just use okay. Maybe we should use EE for energy of an elastic body, or you can use ES for spring. Whatever you want to use. Okay, just make sure you use the right equation though. We worked it out that it's what, 5 joules? Okay. So right now, if I put a bead on that spring and I push it down 0.10 meters, there is a potential energy in that system of 5 joules. As soon as I let go, what's going to happen? The bead is going to fly up. It's going to shoot up. That energy is going to be converted into initially kinetic energy only. Well, actually, it's going to be converted to both. But at some point, it's going to have maximum speed, and at some point, it's going to have maximum potential energy. So, if you think about projectiles, right, this bead is going to go from a height. So once the spring is fully back to its normal length, right? So here it's being compressed. Here it's back to its normal length. The bead is going to be at its maximum speed. And then we know from projectile motion, it's going to go up, and at the top, it's going to what? It's going to stop. So at the top, its kinetic energy is what? 0. But it's also at its highest point, which means it has its maximum what? Gravitational potential energy, right? Okay, so let's look at the first question. Actually, let's look at the second one. What's the maximum speed? So this is how much energy it has. That's going to become its kinetic energy. So the energy of the spring is going to equal the kinetic energy plus the potential energy. I want you to think about that equation for a second before we move forward. Yeah. Yeah. I want you to think about that equation for a second. Yeah, but here's the thing. Right. So we already know what the energy input is, right? What is it, 5 joules? Can't be more than 5. Can't be. Can't be more than 5. But here's the thing. What is that 5 joules going to be converted into? Kinetic energy and potential energy, right? Now, at some point, like for example, let's say at this point here. Let's think about this. At this point here, has it moved vertically? Okay. So, does it have this kind of energy? Okay. Is it moving? So, does it have this kind of energy? But what do they have to add up to? 5. Has to add to 5. Correct? Okay. So, what's wrong with this pen? Oh, no. Hello. The word is not responding. Oh, there we go. Okay. So this is 1/2 mv squared, right? And the equation for EP, or no, I used EG, sorry. Sorry for the confusion. I used EG, not EP. It was mg what? Yeah, mgh. Or delta H, right? Change in rate. Okay. Has to add up to 5. Right? Okay. So, 5 joules is equal to 1/2. What's the mass of the bead? 0.05. Okay. What's the mass of the bead? 0.05 times 9.8. Now, where do you think will be the maximum speed of the bead? Right when it leaves. So let me ask you a simple question. what would it be its vertical change in height at that point? You sure? Right here. I haven't put it in yet. I'm going to put it in, but I want to ask you I want you to think about this, okay? So you take a spring and you compress it 0.1 meters. You let it go. At the moment the ball leaves the spring, at that moment, that's its maximum speed. But it also would have changed how much? 0.1, right? Its change in height would be 0.1. Think about it. The spring is compressed, and then it decompresses, so the bead has actually lifted up 0.1 meters. Uh-oh. Right. Well, we'll talk about it at the end. How much it changed. Right. Now here's the thing. So a question like this is maybe a little bit more challenging. Had I set it up where the spring is like this, and then it's shooting the ball this way, then all you have to do is just set up the energy of the spring equals the energy of motion. But the problem with the scenario that we're looking at is the bead is being shot up in the air, right? So what's happening as the bead goes up, it's gaining what kind of energy? Gaining potential. So we have to factor that in, right? Because the total energy has to be the same. It can't be more, because then you're creating energy from nothing, right? So it actually has gained some potential energy. But again, the energy is going to be still 5 joules in total. So let's simplify. So we have 5 joules over here. I'm going to move this over here. So what actually is all of this? It's a very tiny amount, but still, we should factor it in. It's almost like 0.05, 0.049. So it's not going to make much of a difference, but still we need to factor that in. Okay, so there you go. So we have now the energy on one side. So don't worry about all this. The energy on one side. So 5 joules minus 0.049 should be like 4.9. I'm going to round it off to 4.95 joules is equal to 1/2 mv squared. Now I'm going to get rid of this. I'm going to get rid of the half. So I'm going to multiply by 2 and then divide by the mass. Okay? And I'm going to take the square root of this because it's v squared. So what is v? 44.6? No, meters per second. It has to be meters per second because that's one of the units, right? Okay. Let me give myself a bit more room. Almost. No, one more. Just one more. I'm going to give myself a bit more room here. Okay. My per second disappeared. Okay. Now, okay, is this not correct then? So the top is about close to 10. So the top is 2 times 5, close to 5. So top is about 10. Yes? Sorry? Okay, so if we refresh our memory, so before I did all of this, you remember, okay, So sometimes I get ahead of myself. So got rid of the half by multiplying on this side by 2. And then I divide it by the mass. Okay? And then we take the square root of all. So is it not 44? It's 14? Okay. 14 point, we'll just say 14.1 meters per second. Okay, that's fine. Don't worry about it. Now, that's the maximum speed. Okay? As it goes up, you know from projectile motion it slows down. The maximum height is when the speed is 0. So here's the thing. If we go back to the equation where the energy of the spring has to equal the kinetic energy plus the gravitational potential, right? If we think about this equation again, where the amount of energy is the same, it doesn't change. It's just getting converted, right? At the top, what's the kinetic energy? 0. Now the energy of the spring is still 5. At the top, the kinetic energy is 0. So that means that at the top, it's all what? It's all gravitational potential, right? So at the top then, we have 5 joules of energy, because that stays the same. Now we're going to figure out the change in height. So we're going to divide by mg, right? We're going to get rid of the mg, so we're going to divide by the mass times little g, and that will give us the, should be actually delta H, change in height. Okay, so we have 5 joules over the mass, kilograms times the speed, sorry, times the times little g, acceleration, and that will give us delta H. My 5 joules looks like SJ, or 50J. Not 50J, it looks like San Jose, SJ. I really gotta work. Oh, I said SJ, you said NP? That's pretty cool. Okay. So, it's basically 5 over 1. Because 0.1 times 9.8 is very close to 1. So, it's very close to 5 meters. What's the actual answer, though? Oh, is the mass 0.05? So then my answer is not 5 meters. Really need to, well, okay, get back here. Don't you love these unedited videos when they make tons of mistakes? So the mass was 0.05? But 0.1, why was I thinking 0.1? That's the compression of the spring. Okay. So 5 joules over the mass, 0.05 times 9.8. So that should be 20. Close to 20 meters. Well, I predicted 5 initially. Yeah, so sorry. Double of 5. Did I say initially it was 5 about? So then it should be double of that. So 10.2? Okay. Come on.
Wait, is that including the 0.1 compression?
Okay, that's a good question, and I'll wait for this computer to respond again. So that's 10.2. So this is the change in height relative to the point where we had compression. So initially the spring was compressed a distance of 0.1 meters. Now, if it went up 10.2, it's relative to this compression point. If I said to you relative to the full length of the spring, well, then it would be 10.1 meters, right? Because the spring was compressed at 0.1 meters, so relative to that, it's 10.2. But you could say relative to the point of compression, just 10.2 there. Ladies, that's it. Okay, I'm going to stop the video there. The end. I'm really got to work on editing. Yeah, you heard that.